All right, here are some example problems from page 565 of your textbook. Some proton NMR spectra along with little extra data. Let's look at these. Let's look how we solve NMR problems. Okay, the first one here, compound E. We have a bit of information. The first bit of information is the chemical formula. It is C4H8O2. We are also told that it has an IR absorption at 1743 wave numbers. Now we've had IR before. Right now you should be saying, oh, 1743, I know what that is. 1743 tells us there's a carbonyl in here. Okay, so we've got a carbonyl in here. We've only got 4 more carbons to go. Let's see. What can we determine here? Here's a little tip. First of all, you need to find the best way that works for you in order to solve NMR spectra. Here's the way that works for me. I always like to start downfield, start at the left, and move my way to the right. Mainly being because all the interesting stuff is on the left. All the boring stuff, saturated alkanes, are on the right. So if you start at the right, okay, saturated alkane, big deal. But let's start with the interesting stuff. So I tend to solve from left to right. You do it whichever way works for you. So here's what I'm saying here. As I look down left to right, I see, okay, at 4 ppm, there's some sort of signal here. And recall, we need to analyze it for all 3 things: chemical shift, integration, and spin-spin splitting. All right, so first thing, it integrates to 2. Now, there are various ways something can integrate to, but one of the most obvious ways something could integrate to 2 is if it is a CH2. A carbon with 2 hydrogens on it, a CH2 is the most obvious way to have something integrate to 2 equivalent hydrogens. Okay, doesn't mean I'm right, but that's the most obvious. Next thing, chemical shift. It's down at 4 ppm. What could bring it down to 4 ppm? And before you start thinking all halogens and fluorines, recall that we're given the formula C4H8O2. What's the only thing in there that could bring it down to 4 ppm? Oxygens can. So that tells me, that leads me to believe there is an oxygen next to that CH2. All right, good deal. Chemical shift down to 4 means oxygen next to the carbon containing those hydrogens. Integrates to 2, CH2. Spin-spin splitting. Note it's a little close together here. I can't quite see what's going on. Luckily, they have blown it up for me. They have expanded that. And what do we see here? A 1 to 3 to 3 to 1 quartet. Well, 1, 3, 3, 1, 4 peaks. That means 3 hydrogens next door. What is the most obvious way to get 3 hydrogens next door? A methyl group. A CH3 is the most obvious way. And now you're saying, well, wait a minute here, Watson. Couldn't you have a CH2 on one carbon and then a CH on the next carbon? Well, that would give you 3 next door. But note, this carbon already has 1 bond to oxygen, 2 bonds to hydrogen. It can only have 1 more bond. So there can only be 1 carbon next door to it, and that carbon must contain all 3 hydrogens in order for this to make any sense. So we've got OCH2CH3. Now check this out. With this one peak, this is the first peak we looked at, we've already got OCH2CH3. Now, at this point, we could use our brains or we could just keep plugging along. It's up to you. But let's just keep plugging along, shall we? We've got OCH2CH3, we have our carbonyl. Okay, that's this peak. Myopic Turtle got bored. Myopic Turtle already knows NMR. Okay, so moving on down. Going upfield from 4 ppm, we've got a peak at 2 ppm. What do we see here? Well, It integrates to 3. What's the most logical way something will integrate to 3? Well, I think a CH3 is the easiest way to integrate to 3. All right. It's a singlet, spin-spin splitting singlet. So whatever is bonded to it next door, if it's a carbon next door to that CH3, that carbon would have no hydrogens on it. There's no spin-spin splitting. It's a single peak, which means 0 hydrogens next door. Now, that's if it was a carbon next door, there would be 0 hydrogens on it next door. There could be an oxygen next door, and then it would be a singlet. But note, an oxygen couldn't work, because if there were an oxygen next door, what would be the chemical shift value of these 3 hydrogens? Yeah, if there's an oxygen next bonded to this carbon, those 3 would come way down here at 4 ppm, but they're not at 4 ppm, they're at 2 ppm. Well, what will bring resonance down to 2 ppm? Because saturated alkanes are about 1 ppm. What will bring it down 1 ppm in value down to 2 ppm? Well, if you look at our sheets, we find carbonyls can do that. So at this point, I am betting that this CH3 is bonded to that carbonyl. Now we're just going to stop here with this one, because let's look at this. We know we have a CH3. We're pretty much guessing, have a good guess we have a CH3 here. We know we have a carbonyl here. We know we have OCH2, CH3. If you look at the 3 pieces of our molecule that we have, you see that that is 1, 2, 3, 4 carbons. Okay. How many hydrogens here? 1, 2, 3, 4, 5, 6, 7, 8. There's our 8 hydrogens and our 2 oxygens. Those are all the pieces of the molecule. There's no extra pieces of this molecule. That's it. So at this point we have to use our brains. How can we put this together? Well, we've got 3 pieces. There's really only a way to put them together. Because note, you can't put the CH3 in bonded to this oxygen. We already mentioned the CH3 cannot be bonded to the oxygen. It would be down at 4. So what's the only thing that can be bonded to this oxygen? The carbonyl. And so then what has to be bonded to the carbonyl? That's CH3. So there's our molecule. Oh, that's not written very fun. What would be a better way to write this? Oh, how about this? CH3, C double bond O, OCH2, CH3. There it is. And so note the power of proton NMR. This is a situation where I could have been walking by in the lab, saw some white powdery substance on the balance. That could have been anything. It's a white powder. Who knows what it is? Running the IR, oh, I know it has a carbonyl. Stick it in the NMR, run the proton NMR. By the way, on our instrument, proton NMR is going to take me about, I don't know, actually a total of about 1 minute to run it, and then about, because I've done it so much, 1 minute to process a spectra. So in less than 10 minutes, I've gone from finding this powder on the benchtop, not knowing what it is, to finding out what it is. I've got the exact structure of it right there. Little disclaimer, this molecule is ethyl acetate. It's actually a liquid for you purists out there, but you get the idea. I found a liquid on the balance. And there's a structure. NMR gives you the structure of the molecule. From what's this unknown powder? What's this unknown liquid? I don't know. Run the NMR and the IR, and now you know what it is. Cool. But let's keep going on this spectrum, though. There's an issue here. We never even looked at this. We never even looked down here. We didn't need to. NMR, proton NMR, gives us redundant information. Recall that this peak here at 4 ppm was at 4 ppm because it was next to an oxygen, integrated to 2 because it was a CH2, and was a quartet because there's a CH3 next to it. This CH3 had to be somewhere in the spectrum. Where are these 3 hydrogens? Well, that's them right there. Why is it a triplet? Why it integrates to 3 because it's a CH3. Why is it a triplet? Because there are 2 hydrogens next door. those two hydrogens next door. So there's almost a little self-check in the NMR spectrum. All right, I got this molecule, but I didn't analyze that peak. Does this peak here lead me to the same molecule? Does it check out with what I'm proposing as my structure? Yes, it does. Okay, let's move on to the next spectrum. All right, let's look at this one here. Note, the instructions tell us it is also C4H8O2. Note, it also has a 1730 IR peak, and therefore we also are fairly confident there's a carbonyl in there too. All right. Start downfield. Okay, so, okay, we got this peak here. 4 ppm integrates to 2 singlet. What does that mean? Well, integrates to 2. That's telling me CH2. It's at a chemical shift value of 4. Well, what would bring it down to 4? You look at our table. Oxygen brings it down to 4. What's on the other side? This carbon is bonded to 2 hydrogens and oxygen. That's 3 bonds. It needs one more bond to something. What could it be?